Hey, welcome back everybody to 10 of Codes. Today we're going to take a look at how we can send an EIP-1559 transaction. This transaction is just going to be simply transferring Ether from one account to another. In the next video, we're going to take a look at how we can interact with smart contracts, but with this one, let's just focus on transferring Ether. With that being said, if you have not checked out the previous videos that showed you how to connect to an Ethereum node, as well as work with wallets, please check out the videos. I will include the links down in the description. It will give you a lot of context around where we are at right now. With that being said, let's jump straight into the video. Alright, so we have our boilerplate main.go file. Within the imports, let's go ahead and import all of our dependencies. We want to start by importing context as well as the crypto ECDSA, and then FMT and log for logging purposes. And we're also going to need the math/big to go ahead and specify our gas prices in the form of big integers. And we're also going to need all of our Go-Ethereum dependencies, starting from the ETH client, the types, the common, the crypto, and the params, as well as the RPO. Again, make sure you are typing in terminal go get followed by the URL, the GitHub URL, so these dependencies are available for you to use locally. Alright, so once you have specified your imports and grabbed them from GitHub, let's go ahead and start building out our main function. We're just going to keep everything within here just for this purpose. You can break it up as you wish. So let's start by establishing a connection to an Ethereum node. Again, am going to use the Infura endpoint that I was provided with by logging into my Infura account. I'm going to use the Rinkeby network. I do have a test account, two test accounts, one with some Ether, one without. Check out the first video in the series to see how this connection is established. Alright, so once we do our error check, just to make sure there's no errors encountered, let's go ahead and work with our private key to be able to sign a transaction. So let's declare a private key variable, and let's set it equal to crypto.hex to ECDSA, which is essentially going to convert our hexadecimal private key. And I just grabbed this from MetaMask. You can generate this using the Golang method that I showed in the previous videos. Again, check out the link in the description to see how that's done. But for this tutorial, I just went inside of MetaMask, generated a new account, and exported the private key. And you can do the same thing, and once you have that private key, you can go ahead and paste it right here. Again, for production applications, you probably don't want to do this, as this is not a safe thing to do. But for this example, let's just set it into this variable. Alright, so once we have our private key, we want to make sure there's no errors encountered when converting that into ECDSA format. So let's just do if error does not equal nil. We're just going to do a log.fatal, and we'll just pass the error so we can see what the error was. And the next thing we want to do is define the public key, which we can get from the private key. We can do that by saying private key .public, and we can just store that in a variable called public key. Alright, and then we want to continue by casting this public key into an ECDSA format. We can do that by saying public key dot, and then within parentheses we want to go ahead and send in a pointer to the ECDSA, and then we want to set this to a variable. Let's call it public key and ECDSA, and this is also gonna have a flag, and let's just call it OK. And we can check this flag to see if there was any errors, and say if not OK, then there was an error. So we can say log.fatal, and we can say unable to cast to ECDSA. Okay, so then now we want to set the from address to specify who the sender of this transaction is. And let's create a variable and call it from address and set it equal to, let's convert the public key right here that we have in the ECDSA format into an address format that Golang can understand. We can do that by using the crypto library. We can do that by saying crypto.pubkey to address. And we have to pass in a pointer to that public key ECDSA variable. Perfect, so now once we have specified the sender, let's get the nonce of that account. And that nonce is essentially going to be the current transaction count. So how many transactions has this account sent? We can do it by using the client and saying client.pending nonce at, and let's pass in a context and then the from address that we want the nonce from. And let's go ahead and fix this so we have parentheses after dot background. Cool. And then this we want to set to nonce, and then it looks like we also have to catch the error if there is an error. So we can say if error does not equal nil, say log.fatal, and just print out unable to get nonce. And we can just do an fmt.print line here so we can see for debugging purposes what the nonce is. Alright, so next thing we want to do is let's define the recipient address. We're just going to hard code this address for this demonstration purpose. However, you can acquire the recipient address however you like using Go, or even through user input. Let's just create a variable called toAddress and use the common library to convert the hexadecimal address that we provide in the format of a string into an address that Golang can understand. The next thing we want to define is the value of this transaction. So essentially, how much Ether do we want to transfer from our account or from this address that we define on line 40 to the address that we defined here on line 50. So let's just say value, let's set that equal to, and we'll have to use a big integer. So we'll just use big.newInt. So this value is going to be measured in way. So if you want to send 1 Ether, this is going to be 1 followed by 18 zeros. However, we don't have 1 Ether in our test account. As you can see, we only have 0.098 Ether. We're not going to send 1 Ether. We're going to send something very little. Let's just say 1,000 way. Perfect. So now that we have our value defined, or the amount that we want to send, so the next set of variables we want to define is the gas max, essentially the maximum amount of gas we are willing to spend for this transaction. Then the gas tip, also known as the max priority fee. This is the amount that we are willing to tip the miner so they can include the transaction in their block, as well as the gas limit, actually the maximum amount of gas we are willing to spend for this transaction. Again, when you're building more scalable applications, you want to make sure you have a sound way of calculating these values based on the activity. Because again, if the network is congested, these prices may not be valid, as maybe there is a price increase in gas price, which prevents your hard-coded values here to be invalid. And again, this is the Rinkeby test network, so we're not going to see that much of a fluctuation in gas prices. However, when you're working with, for example, the Ethereum mainnet, you might experience more volatile gas prices depending on network usage. With that being said, for this example, let's just work with what we have here. So the next thing you want to define is the data. If we want to interact with a smart contract, we would have to send byte data along with our transaction, which essentially will say, hey, go to this smart contract and change this, or trigger this function, so on and so forth. We're just going to declare an empty variable, which we're going to pass along with our transaction in a moment. So once we've defined our empty data, let's go ahead and build the transaction by saying transaction equals say types.newTX, which is going to allow us to create a new transaction. And let's go ahead and pass in a pointer or an address to a new dynamic fee transaction. We can create that by saying types.dynamicFeeTX, and we'll have to pass in all of the parameters that we defined here, such as the nonce, so on and so forth. So the first thing we want to define is the nonce. We say nonce followed by a colon, and then the variable nonce that we declared on line 42. The next variable we want to define is the gas fee cap, which is gas max, and we can change that here, gas fee cap, to make it consistent. And then followed by a comma, and then the next one we want to specify is the gas tip cap. And again, that will be gas tip, but I'm going to change it here to stay consistent. Let's define the gas limit, or the maximum amount of gas we're willing to spend. We just keep that consistent as well. And then we want to specify the recipient of this transaction. We have this toAddress that we defined here on line 50. And then let's define the value of the transaction. And because we are sending Ether, we're going to specify the value that we defined on line 52. And then we want to specify the data. So data, and then We have data here defined on line 56. And because we're not interacting with a smart contract, it is an empty array of bytes saying cannot use to, we need to pass in the address of this address. So we just do ampersand. And then this is saying, okay, we haven't used it. All right, perfect. So we have constructed a transaction that uses all of the variables that we defined previously here. So now we're ready to sign this transaction. We're going to do this within the main function. Obviously, with scalable applications, you want to either outsource this or handle this better. But for this demonstration purpose, we have our private key here, which we defined on line 26 that we're going to use to sign the transaction. So in order to do so, let's go ahead and build a new London signer to sign this EIP-1559 transaction. We're going to get the configuration from params.rinkeby chain config because we are using Rinkeby. And then we want to specify that we are working with the London block. We can do that by saying params.rinkeby chain config.london block, and then that's going to store it in the block variable here. So now that we have our configuration and the block that we're going to work with, let's go ahead and build a signer with these two variables. So we can do that by saying types.makeSigner and pass in the configuration as well as the block, which is the London block we defined here. And this is going to be stored in a variable, let's call it signer. And then we can trigger the actual signature of the transaction by saying types.signTX, and then pass in the transaction that we want to sign, and then the signer that we want to sign it with, and then the private key that you want to use to sign the transaction. So once we trigger this is going to return to us a signed transaction. We can just store it in the signed transaction variable here. And then it's also going to have this error variable. So let's just do a quick check on that. So we can say if error does not equal nil, we can say log.fatal unable to sign transaction. If you ever wanted to examine the hash of this transaction, you can do that by saying sign transaction.hash and then convert that value that's returned into bytes. And let's just store that into a variable called hash. We can also get the raw representation of this transaction by using the RLP library and saying RLP.encode to bytes and passing in the signed transaction. This is going to return two values. One is the raw transaction and a possible error. Let's just do a quick check on the error and see if it was successful or not. And then we can go ahead and print out these values by using printf. Alright, so once we successfully built this transaction, let's use our client to go ahead and send it to an Ethereum node. So say client.send transaction. And we'll have to pass in a context and then followed by the signed transaction that we just created. And this is going to return a possible error, which we can check if it's nil. So we can say if error does not equal nil. Alright, so once we've successfully sent the transaction, what we can do is print out the transaction hash, which we can use to look up that transaction using a block explorer like Etherscan. We can say fmt.printf and then say transaction sent followed by the hash of the transaction. So we can say signed transaction dot hash and then convert that into a hexadecimal format. Perfect. So far this looks good. So let's go ahead and use terminal to run this application. And you'll see that we're looking for the transaction sent output followed by the transaction hash. So let's go ahead and copy this. And if we head over to the Rinkeby testnet explorer and type in the transaction hash, you can see that it was submitted and it was successfully mined 29 seconds ago. So let's take a look at how the gas prices were used. So right here you'll see that we used 95% of our gas limit, which was 22,000. Our base gas fee was 11 Wei, which is essentially the minimum amount that we have to pay. And then our maximum amount that we were willing to pay was roughly 38 Gwei, which we defined here again on line 54 as the gas fee cap. And then our max priority or the tip was here 3.8 Gwei. We were willing to pay the miner, which again is defined here on line 54 as the gas tip cap. And then we used it here to build the transaction. And as you can see, it picked it up as an EIP-1559 transaction, which is what we were looking to do. Anyways, that is how you build and send an EIP-1559 transaction that transfers Ether from one account to another using Golang, Again, this is a very basic implementation. There are a lot of things that need to undergo hardening, such as how you handle the private key and signatures. However, I hope this really helped you get an idea of how transactions are built, signed, and sent using Golang. Thank you much for tuning in. Again, if this video was helpful or you learned something new today, make sure you give it a like, comment any thoughts that you may have, and make sure you subscribe and click on that notification bell so you are notified every time I drop a new video. I will see you in the next one.